Welcome to another eDrilling webinar. Today's webinar is how to set up your digital twin. So today we have Svenning Ødegaard, or the CEO of eDrilling, and me, Morten Svendsen, that is going to go through this webinar with you. There is a question box in the GoToWebinar application, so if you have any questions, please fill them in as we go along, and we'll have a Q&A in the end of the webinar. Well, let's start about the concept of a digital twin. There's a lot of different definitions by people in the industry today, but the concept of a digital twin was first introduced by Michael Greaves at the University of Michigan in 2003 throughout his course on product lifecycle management. From our side, we think that the definition that Halliburton has is that the digital twin essentially creates the physical reality and the physical assets and put them together in a form that's digitally accessible. So we think that's a very good explanation of what a digital twin is. So some of you have seen this before. It's the history of eDrilling and what we have done when. And actually, the first digital twin was introduced by us in 2008 in a commercial application. So this is proven technology seen from our side. So, as you know, when you are drilling a well, you have the physical well with the real-time data signals from the rig. And together with that, and together with the information you have about the well, as the survey, the tubular, the formations, and so on, you are able to have focus on your well and run monitoring on your well. But we use the same configuration to create what we call the digital twin. And for us, the digital twin consists of dynamic mathematical models, which is linked together in an integrated drilling simulator. And this enables predictive analytics and real-time diagnostics. And to do this, we use historical data, real-time data, and real-time simulations. And kind of the digital twin is then possible to be visualized in a normal plotting tool and also in a 3D environment. So when you're thinking about a digital twin, are we expecting one-egged twin wells? Well, when you are building up your digital twin, the quality of that is depending on the input data, of course. But it's actually the differences from the real well and the digital twin that is interesting, because that is what we are building the diagnostics on. So the differences or the deviations that we see while drilling is actually a sign that something might be wrong. So the digital twin is, from our perspective, a part of our virtual well. And the virtual well consists of the digital twin, which again is integrated drilling simulator having dynamic models for hydraulics and temperature, torque and drag, and also an ROP model. To be able to see what's going on, to see the results of the digital twin combined with real-time data, we use a virtual well visualization in 3D, where we can make the invisible visible. We can display the results together with the risk register for the well. We can give a better understanding of what's happening and build a good communication tool that can be used throughout the team that's doing the work. Here are some digital twin samples. lately. So these are wells that are either running a digital twin at the moment or have been running this lately. So it's a good combination of fixed platform, jackups, and floaters. So let's talk a bit about the topology of how everything hangs together. In the normal kind of the monitoring of the wells, a real-time data feed is sent from the rig to a data store. Very often a WITSML data store. This could be Sitecom, or it could be Petrolink, or it could be Halliburton or Schlumberger or whoever. And very often these data has been looked at through applications from the different vendors. So what we are adding here in combination with, which is already there, we add our digital twin, which we are running in this example in Amazon Web Services. So there we run our digital twin or our simulation package is run there, driven by the real-time data from the rig, and also we import data from the client data warehouse. This is like the configuration of BHAs, directories, and so on. And we also have it, of course, we have our own application for visualizing the data. But we can also write the results back to the WITSML data store and make it available for all the different parties involved in the operation. So, setting up the digital twin. Here's just a couple of points of what we actually do. So what we start with is that we import data from the client data warehouse. We do a quality check on that imported data. We connect to the real-time data stream, and then we set up the visualization. So I will start by looking at the configuration data that we are using. So this is our tool for looking at the configuration data. And I can go here and do a WITSML import from a data warehouse. Now I'm connecting to one of our clients' data warehouses, and I can just browse to a well that I know have some data. And here I have kind of rig data. I have here is missing tubular data. I have some fluid data, trajectories, and wellbore geometries. And this I can just import by pushing this button. I have already imported data to this digital twin. And you see you have some formation data, pressure profiles, temperature profiles, the trajectory, and so on. So all the data that I need for doing this, setting up this digital twin is already gathered. Now I would like to run a data quality check. And I get an error message that there is something wrong. And it says that the tubular weight of component 3 might be too high. And then I press OK, and it's actually showing that this is the one which is wrong. So now I will change it to what I know is the correct one. And then I can do it again just to verify that it's OK. So now my data quality check was passed. So now I have, in theory, built up the configuration of how the well looked like. So the next step here would go and connect to the real-time data. And to do that, I have a web interface to our Amazon Web Services server where I do all this configuration. So here I would add the path for where the WITSML real-time log object is located. I have my logging details, and I also select the log or the logs that I want to connect to. At the same time, here you see in the background, you see some data moving around, but this is actually some data from the digital twin. So this is calculated ECD in real time. And I also can set up my output manager, which is also writing back to this company's WITSML data store. So I'm writing back diagnostics. I have a time log that I'm writing to. I also have a depth log. So this is quite just briefly how we set this up, and it's quite simple to do. So now I would like to have a look at the the normal plotting tool to look at my digital twin. So here I have my plotting tool, and I can see here I have some calculated ECDs. I have calculated and measured standpipe pressure. As you see, we have a deviation here, so we have actually created some diagnostics messages. And I also have some depth profiles of my well with complete ECD for the entire well with the pressure window, for example. I also have my torque and drag simulations. So here I've been running a torque and drag evaluation. Then I just do it from here, get this window up, and I can run this torque and drag evaluation. Then it runs it, and these are the lines that was created from that. These points are automatically picked up from the lift and slack and free rotation operations that they do on the rig. So then you have a roadmap showing you how your hook loads should be, for example. We also do real-time hook load and torque simulations. So you have your digital twin and the real measurements to compare with. So, but this is kind of the standardized way of looking at data as everybody else is doing. So let's go to the next thing and set up the visualization. So this is the 3D visualization tool that we use to look at our digital twin. And as you can see here, we have a directory here. And if I zoom in to the bit, I can also start seeing that they have some virtual sensors from my digital twin. And I can also look at my BHA. And right now it's not rotating and they're not drilling. So they're standing still at the moment. But here, from here on, I can add more information. I can, for example, add my formation layers, and I get some more information here. And now I don't only have, so I have all this kind of data. The formation layers is imported from Petrel, and here in the background you can also see a fault that is imported. You can also add the rest of the trajectories or the wells from the area, and now you actually have also a better view of where your well is located compared to the other wells in the area. I will again zoom into my bit, and here you can also see I could add even more information. I can add this information object, which is actually imported from the risk object. And here you see information about what to expect downwards in the well. For example, there is a possible loss area, possible fault, and also other information up here. So you could also add information as it happens. Like, for example, up here there was a stringer. You could also, on the right side here, you see we have some gauges which we are set up with different parameters or measurements, and also from the digital twin to make sure that we have a good control of what's happening in the well. I could also zoom out a bit more and add, for example, a plot along the wellbore with my ECD, for example. Then I have a plot showing me the ECD of the entire well during the operation, which is updated in real time. Yeah. I think maybe we could see if have some questions. Yeah. So let me see. Next slide. So while we have got some questions there. Let's start with the first one. For running the multiple models together in sync and to be able to make predictions in real time at every given instant in time, how complicated are your various models? I'm talking from a point of view of being able to run the models fast regarding the accuracy of predictions, and how real time are the predictions that you make? Do you predict into the future? We have our own synchronization of our models that we have, and we have incorporated the temperature model into the hydraulics model, so that is all the time updated as tightly as possible. But we also have an interface between the hydraulics model and the torque and drag model to be able to transfer the fluid properties to the torque and drag model to get the realistic or the correct mud distribution and temperature and so on. So there is a very tight interaction between the models. And when it comes to how real time we are working, we are typically running our infrastructure in 1 hertz speed, or we do a calculation each second. And that is basically driven by the real-time data that we receive from the rigs. And we say that we need to have a minimum of updates each 5th second, but we prefer to get it as quick as possible, and that is very often close to every second or every second. And when you talk about real time, it's also kind of interesting to see, because of course there are lag, because this is running in a cloud environment and not on the rig, directly on the rig with the control system, but it's on the outside. So, but the lag time that we see is very often not in the transfer between us and the data store, but it's very often from the rig to the data store. And
when it comes to if you are looking into the future, there's an instant of the simulator that's running automatic forward looking, which means that we are predicting ECD and torques ahead in a 1 second interval. We can also quickly go in and do what if scenarios, where we then have a calibrated simulator that we can do what if scenarios on.
Yeah. Yeah. What is the main difference between your system and other systems that currently in the market, like those the mud logging companies have? The biggest difference between us and a mud logging company is that we try to do everything automatically. We are not trying to replace any personnel. We are trying to achieve better support. We are trying to do automatic diagnostics, telling the mud loggers or who is using the system what is actually happening in the well. So we don't only look at the real-time data, but the most important thing that we do is actually the digital twin and the deviation between the digital twin and the real well.
As far as we know, we don't see any mud loggers doing digital twins. We don't see any mud loggers doing a dynamic modeling of the process during. They can do some static modeling during operation, but we think this is the future of how you operate and follow the operation.
And very often in the mud logging systems, the alarms that they have is on fixed values with fixed limits or limits that they change. But for us, it's all driven by our digital twin or models. Yeah. What is the certainty in percentage? Do you have tested before and demonstrated your simulations were well done? We have been doing since day one. Our main goal has been to actually verify and make sure that our system is accurate. And we have been doing a lot of verification processes with many of the big oil companies for a long time, where we have been benchmarking, of course, towards other simulation tools, but also on real-time measurements. So we can say that we have a very high accuracy, and we have been verifying that for a long time. So let's see if there's any more questions.
There's a question here related to cloud solution. Could we run it on other than Amazon Web Service? Of course, we can run it on a private cloud for a company. We can, of course, also run this on an Azure. solution from Microsoft, or we can run it on specific computers at the different customers.
Yeah. And yeah, there is also a question: where is the real-time processing being done? And kind of next is it in the cloud? And that is the thing here. All our processing is done in the cloud. So all our calculations or modeling of the digital twin is done in the cloud environment. And that allows many kind of users or applications to plug in to actually utilize the data that we have available. There is another question here: what are the engineering applications engines you use to make your engineering analysis? So we have our own applications that we use, and this is our real-time application that we did just show you, and that is built, the foundation of everything that we do is our models that we use to model the digital twin. And these models are, when we started making them, the focus was that we would like to have models that was dynamic, that we could run in a real-time environment. And from there on, we have actually developed applications for planning when it comes to hydraulics, well control, kick tolerance, and torque and drag simulations, but also training. So we have a downhole training simulator that we can plug into topside drill floor simulators or just run as a engineering simulator. Yeah. And yeah, another can you incorporate the geological model given by seismic to your modeling process? So when it comes to kind of geological models, we can import for us our view from various tools to visualize the geological how it looks like. But we use the geological data that's available for kind of when it comes to formation, positioning, formation hardness, densities, but also kind of pore pressures and frac pressures and so on. So we incorporate all that into our system and use it for our modeling and diagnostics.
So as you also can see on the picture, we can also take seismic images into the system and use those during geosteering.
Just try to see which questions we haven't answered yet. There is a question about, do you have any data analyst tools in the software, the plots and so on? And what we have is, I showed you this kind of the plotting tool that we have. And what you see is this is the typical thing. You look at the real-time trends, and you also look at the real-time trends from our digital twin in combination. And this is the framework, and this is something that everybody is familiar for everybody. If the data is available, we can plot it, and if it's available, we most possible can also get output to compare it with from the digital twin. And this is also the place, as Sven Inge talked about, we also do what-if simulations from here. And then we can trigger our simulations based on the instant digital twin that we have with the cuttings distribution, the temperature distribution, the hydraulic, the fluid distribution, and continue a quick simulation on the side where you can do some changes to see how this would affect your well. But our preferred way of looking at the drilling operation is actually in this 3D environment. And this is also something that we have got a lot of requests from the beginning when we started this work, was that they would like to look at the well, how it actually looked like, and not only on squiggling lines.
Yeah. So do not present a new system with squiggling lines. So Morten, if you zoom into the drill bit now, this is how we foresee how we think all drillers should be looking at their drilling process. They should have a view like this. Normally today in their control system, they look on trends either from the cyber-based system and the mud logging system and so on. It's duplicated data, but they don't focus on the downhole. So we foresee that every driller and every driller's cabin should have this and be able to look on the risk and look on the real-time data, what's happening downhole.
So, and we can split the screen so we can have focus on different things that we have. Here we have, for example, our FIT and we have the casing shoe pressure. We could also split it into a third screen, and then we could have focus on if we have a BHA element that we would like to have focus on going through hard or tight spot positions and so on. And this is rendered in real time. And we have had success on using this on the drill floor for the driller to actually look at the operation. And also kind of importing not only the risks, but also drilling parameters, changes in drilling parameters. Then the driller can use this as his GPS system while he's drilling the well. So, yeah. I think we are running out of time, so I would really like to thank you all for joining us in this webinar. If you have any questions, please feel free to contact us after the webinar if you have any questions. The presentation is also located in the handout box in this application, and we will also publish the recording from the webinar on YouTube, and I will send you all a link for it afterwards. So thank you all for joining. Thank you, Sven Inge, for helping me.
Thank you, Morten.
So have a great day. Thank you.